Hello and welcome to this webinar on multi-tenant analytics on Amazon EMR. My name is Radhika Ravirala. I'm an EMR solutions architect at AWS. In this session, we will discuss what multi-tenancy is all about and why organizations implement it. We'll dive into implementing multi-tenant analytics on Amazon EMR, specifically diving into 3 dimensions of isolation patterns that can be implemented on the Amazon EMR platform. We'll wrap up with some multi-tenancy with other big data services on AWS that work in conjunction with Amazon EMR, and I'll leave some time for a Q&A towards the end. So what is multi-tenancy? By definition, multi-tenant architectures allow multiple users or groups to share resources on the same operational system. These designs offer mechanisms to isolate data and resources from different tenants or groups of users. They also provide controls to prevent monopolization of resources of the cluster as a whole to ensure that the cluster isn't overwhelmed. The best example of a multi-tenant environment is that of an apartment complex, which gives each tenant his own space while sharing resources like plumbing, shared spaces, security, maintenance, and etc. Yet another common example that you all might be familiar with is that of cloud computing. And the AWS cloud, a number of enterprises, startups, and mid-sized companies have been successfully running their applications in different regions and different AZs. So what's the motivation for implementing multi-tenancy? Businesses share resources specifically in their analytic environments to run workloads, say for example, multiple clients. They also like to support multiple departments on a data lake that they have built. It is also not uncommon to see organizations testing multiple versions of an application or even testing a single application with different data sets. There are, however, quite a few challenges when it comes to implementing multi-tenancy. For example, implementing multi-tenancy at all stages of a pipeline involves having an understanding of the nuances of the processes and tools involved. Metering tenant usage of resources can be a hard problem, especially if the tenants share databases and compute resources. Scalability and time involvement can be difficult as new tenants onboard. And applying robust security controls overall can be a daunting task in many cases. Addressing these challenges requires taking a closer look at some of the key elements in multi-tenancy. These include authentication, authorization, auditability, isolation strategies, scalability, monitoring and performance, a central UI where the tenants can be managed effortlessly, backup and recovery, and finally, metering. These are all some of the areas that the SaaS application builders should look into as they're building their SaaS applications. In an analytics environment, this specifically means applying all those dimensions of the key elements to the entire analytics pipeline, which consists of ingestion, storing, processing, and consumption of data. In today's session, we will explore multi-tenancy from 3 different angles and show how they are applied to the analytics pipelines as a whole. We'll specifically look at user isolation that can be accomplished through authentication mechanisms, data isolation through authorization, and resource isolation through queues and workload management. So let's start with multi-tenancy in Amazon EMR. Some terminology before we start. Broadly speaking, there are 2 different architectural styles when building multi-tenant analytics architecture. They are silo mode and shared mode. A silo mode is where the tenant analytics, which includes data and processing, is fully isolated from other tenants. The constructs that you build are logically unique in this model, meaning that you have a separate representation for monitoring, management, and a completely separate security posture. In the shared mode, tenants tend to share all analytic resources, and this is often a common scenario that we find in enterprises. So here is an example of a silo scenario in Amazon EMR. We have 3 different users, a data engineer, an analyst, and a data scientist, each launching their own EMR clusters. A data engineer installs tools like Spark and Hive to manipulate and store the processed results in S3. An analyst might run tools such as Spark SQL and Presto to explore data sets on the EMR cluster and send the query results to his own S3 bucket. And a data scientist might be using the EMR cluster to run machine learning or deep learning frameworks. The example we have seen previously gives insights into some of the characteristics of the silo model. In this style, as you may have noticed, each tenant is able to launch their own EMR cluster with specific tools for processing and analyzing. The data is stored in tenant's own S3 bucket or optionally on HDFS on their own cluster. The Hive meta store on the cluster can be stored on the cluster or externally on Amazon RDS clusters as well. Now, there are quite a few advantages of this model. As you may have noticed, there is complete isolation. The tenants don't interact with each other at all. It is very easy to meter the usage of resources in this environment. And it can also be a very cost-effective option when leveraging transient clusters and or spot instances from the EC2 spot market. Some of the cons for this silo mode include sharing of data across clusters, especially if you are storing data in HDFS. It's often hard to share the data across multiple tenants. And for a long-running cluster, this model can get very expensive. But in many organizations, a shared scenario is more common. Sharing clusters between organizations is a cost-effective manner for running large Hadoop installations, since this allows them to reap benefits of economies of scale without having to create private clusters. A large multi-node cluster, such as the one shown in this picture, with all the tools and frameworks installed, can support a variety of users. In addition, this infrastructure can also be used by end users who can launch edge nodes to run their own data science platforms. Despite the cost effectiveness of the shared scenario, sharing a cluster can be a cause of concerns, as a tenant might tend to monopolize resources and cause the SLA to be missed for other tenants. For example, an analyst can issue a long-running query on Presto or Hive, and much of the cluster resources are consumed by the tenant. Or a data scientist might train a model over massive amounts of data that can span many hours or many days. Now, let's look at some of the strategies to address some of these concerns and how they are implemented in Amazon EMR, starting with user isolation. The user isolation allows the admins to prevent users from viewing or accessing other tenants' data or their resources. So in terms of authentication on Amazon EMR, if you are submitting a Hive job or a Spark job, you can leverage that. You can submit that job using an AMR step API. And to do that, you can use the AWS IAM credentials. Similarly, if you are an admin or a user who wants to SSH as a Hadoop user into the master node, you can do that using an EC2 key pair. And for applications that are running on EMR, you can leverage the LDAP authentication. For example, Hive Server 2, which is a service that enables clients to execute queries against Hive, supports multi-client concurrency and authentication. Spark Thrift Server, that allows you to run JDBC and ODBC clients for Spark SQL queries, is also very effective in enabling user impersonations so that the SQL queries run under the identity of the user who actually initiated the query. Apache Shiro is also a powerful and easy to use Java security framework that is used when you want to authenticate users to your Zeppelin server. Late last year, Amazon EMR also introduced the support for Kerberos. Now, Kerberos is a network authentication protocol created by folks at MIT. It uses secret key cryptography to provide strong authentication so that passwords or other credentials aren't sent over the network, removing any potential threat of an attacker sniffing on your network. So let's look at some of the components of Kerberos. So in Kerberos, the services and users that need to authenticate are known as the principal. Now, the principals exist within a Kerberos realm. Now, within the realm, a Kerberos server known as the KDC, as indicated in the schematic, provides a means for the principals to authenticate. The KDC consists of an authentication server, a ticket granting server, as well as a database. It maintains this database of principals within its realm, their passwords and other administrative information pertaining to each principal. The KDC authenticates these principals and users by issuing tickets for authentication. So how does it actually work? So when a user on a Kerberos network logs into a system, their principal is sent to the KDC to request for what is called a ticket granting ticket, or TGT. The KDC then checks for the principal in its database. If the principal is found, the KDC creates a TGT, which is encrypted using the user's key and returned to that user. The client machine then decrypts the TGT using the same user's key. Now, one thing to note here is that the user's key is only used on the client machine and not sent over the network. Now, there is a common scenario for establishing what is called a cross-realm trust. That common scenario is established typically to authenticate users, say from an Active Directory domain, so that they can access the EMR cluster as themselves. So here is a high-level picture of how the cross-realm trust works with a Microsoft Active Directory and a Kerberos EMR cluster. So when you create a Kerberos EMR cluster, EMR creates and configures a cluster-dedicated KDC that runs on the master node. EMR configures Kerberos for all the applications components as well as any subcomponents that it installs on the clusters so they can authenticate with each other. Now, to set up users who can authenticate using Kerberos, you can establish the cross-realm trust with your Active Directory server on-premise. So once the users are authenticated, it is imperative to think about what data assets they are authorized to use. Again, there are a number of mechanisms within Amazon EMR to authorize access to the data assets. For example, in the storage world, you could use ACLs on HDFS or EMRFS for storage authorization for your data assets on S3. You could also use SQL-based ACLs on Hive Server 2 and Presto to restrict users from accessing specific Hive tables. Similarly, for cluster level access, you can leverage fine-grained access control provided through cluster tags. In today's session, we will focus on EMRFS authorization for your data in S3, as well as some fine-grained access control that you can establish using the open source Apache Ranger project. So a quick primer on EMRFS. EMRFS is an implementation of HDFS that sits between EMR and S3 and allows you to write or allows EMR clusters to read and write files to S3. It offers a couple of neat features. It's called consistent. Those features are called consistent view and encryption. As you all know, S3 is eventually consistent, and this eventual consistency can cause issue for certain types of ETL workloads. As an example, if you are adding objects through an ETL process to Amazon S3 bucket in one operation, and then immediately listing objects in a subsequent operation, there is a chance that the list and the set of objects processed may not be current. To address this challenge, EMR team has released this feature called Consistent View for EMRFS. Through EMRFS, we maintain a consistent list of the objects in S3 through a DynamoDB table and provide the operations running on Amazon EMR to have a consistent view of the objects as they appear on S3. Now, when it comes to authorization, there are a couple of choices that can be implemented in EMR. One is at the storage layer and the other is at the service layer. By default, when you launch an EMR cluster, whatever policy that is attached to the EC2 role on your EMR cluster determines the data that can be accessed in S3. With EMRFS authorization, you can now specify IAM role to assume when a user or group uses EMRFS to access the objects in S3. What it essentially means is that for your users and groups in your Active Directory, they can be mapped to a corresponding IAM role on the AWS platform, which gives them access to specific S3 buckets or specific S3 prefixes. So here is a high-level picture of how the EMRFS storage authorization looks like. In this example, you have two different users belonging to two different groups, and these users and groups are coming in from your Active Directory on-premise or running on the AWS platform. And these users are mapped to corresponding IAM roles that gives them specific access to their own buckets. And this EMRFS authorization can be easily configured using the security configuration component of the EMR management console. So here is a snapshot of how it looks like once you set up Kerberos and EMRFS authorization from the EMR console. It can also be configured using CLI or SDK. Now, storage-based authorization is great, but oftentimes customers want fine-grained access control over their tables or even column-level access to their data sitting on S3. And so to aid those customers who are looking for a much more fine-grained access control, they could launch Apache Ranger on an EC2 instance. Now, Apache Ranger is a centralized framework for data security across the Hadoop platform. Some of its the highlighted features include a UI where authorized users can define and manage policies. It provides fine-grained authorization across many Hadoop components, including Hive, HBase, Tom, Knox, Kafka, and Yarn. It has a central auditing and reporting module where companies can take a look at who accessed what table at what time. Ranger also provides agents to sync policies and users as they are added on the fly. And it has plugins that are responsible for authorizing access and auditing the activity of the users. So here is a pictorial representation of how it works. So Ranger consists of a centralized web application at the core. And this application essentially has three built-in modules. There's a policy administrator, there's an auditing module, as well as a reporting module. Now, the admins and the authorized users can manage security policies either through UI or through REST APIs. The security policies are enforced through a lightweight Ranger Java plugins. Now, the way it works is when you issue a Hive query, that query is intercepted by the Ranger server, checked against the policy administrator to make sure that that particular user has access to the tables and the columns requested in that query. And if the user is an authorized user, his query is run on the cluster and the results are returned to him. So far we have looked at data isolation, but there is also the concept of resource isolation when it comes to analytics, and especially in Amazon EMR. So to understand how resource isolation works, we need to take a trip back in the history. So initial deployments of Hadoop, also known as Hadoop 1, focused on batch-oriented workloads. And if you needed to run multiple workloads at the same time, you were forced to split your clusters. With the introduction of Hadoop 2 and Yarn, new scheduling algorithms that were introduced allow multiple workloads to run on the same cluster, accessing a common data pool along with your hardware and software resources. Now, the Yarn is a very important technological innovation that made it easy to implement multi-tenancy in the Hadoop environment. So what does it exactly do? So Yarn essentially consists of two components. There is a resource management component and a scheduling and monitoring job component. The scheduler is the one that allocates resources to applications running on the client, on the cluster, and the cluster scheduler is specifically designed for multi-tenancy and scalability. Yarn allows you to choose from a set of schedulers. More widely used are two types, a capacity scheduler and a fair scheduler. On Amazon EMR, capacity scheduler is the default one, although fair scheduler is also very commonly used in many customer environments. Fair scheduler in its simplest form shares resources fairly among all the jobs running on the cluster. Now, these schedulers provide an abstraction called queues to share the cluster resources among multiple tenants. So the applications that run on these clusters are assigned to specific queues, with the root being the parent of all queues. These queues that are created can correspond to priorities, to regions, departments, users, or any other parameter that makes sense to a business. So here is an example of how a Yarn queue might look like. So as you can see, the root is the parent of all queues, and you can define additional queues or the children of the root queues based on various departments, geographical locations, users, groups, or priorities. And what you see on the right-hand side is a JSON configuration that can be supplied during an EMR cluster launch, where you can specify the number of queues that you want to create, as well as the capacity that you want to allocate to each of those queues. Again, this is an example of capacity scheduler, and you can create a similar one for the fair scheduler as well. The fair scheduler also supports the concept of hierarchical queues. In a fair scheduler, the available resources are distributed among the children of the root queue in a typical fair scheduling fashion. Then the children distribute the resources assigned to them to their children in a similar fashion. Now, you can assign queue weights to control that the queues get a fair share of apps, or each tenant gets their fair share of the resources of the cluster. In addition to that, you can also manage access to the queue using ACLs, or access control lists. Now we'll shift gears and look at how multi-tenancy can be implemented with other big data services, starting with Amazon Redshift. Going back to our terminology of silo mode, in terms of Redshift, it means that each tenant gets their own Redshift cluster. Data is stored in the tenant's compute nodes, which means they are loading the data into their own compute nodes. You can apply IAM policies and database privileges further to control who has access for each tenant as well. Some of the advantages of going with the silo mode include, just like in the previous case, a complete isolation and fine-tune experience for each tenant. Each tenant also gets to control the number of nodes they want and design it specifically for their workloads. As before, it is very easy to measure the usage and resources consumed by the tenants as they have their own clusters, which is metered for their usage. On the downside, handing out individual Redshift clusters can be very expensive. These clusters must be provisioned as part of the onboarding process, which can be time-consuming. As handing out an individual Redshift cluster to each tenant can get expensive, a more common scenario in customer environments is that of a shared model. In a shared model, tenants can be segregated either via separate schemas or through separate databases. One thing to note when the tenants are segregated through schemas is that the authorized user of a Redshift cluster has access to all the databases within that schema. Now, fine-grained access control can be enforced via a SaaS application to further restrict users or tenants from accessing other tenants' databases. Similarly, when tenants are separated or partitioned through different databases, they can share the database and tables within the same Amazon Redshift clusters. Their data can be partitioned via a column that represents a unique tenant identifier. When implementing multi-tenancy with Amazon Redshift clusters, it is important to note on certain limitations that exist within the service. For example, there can only be 60 databases per cluster, or 9,900 schemas per cluster, 500 concurrent connections per database, 50 concurrent queries, and the fact that access to a cluster enables access to all databases in the cluster. So these are important considerations to think about as you think about onboarding multiple tenants on the same Redshift cluster. So on the plus side, for the shared model on the Amazon Redshift cluster, the overall management, monitoring, and agility due to the use of a single cluster becomes a very easy task. On the downside, as I mentioned, you have to think about the limits on some of the aspects of the service itself, although some of them are addressable through other mechanisms. For example, the concurrent connection limitations can be addressed via a caching layer that can be implemented in front of a Redshift cluster. But other limitations, such as the number of databases and schemas, are difficult as they are hard limits, and it becomes hard to scale as you onboard many customers. Security as well becomes a challenge as multiple clusters need to access data in the same cluster, sharing the same database or tables. So when it comes to user isolation in Redshift, there are two important resources to think about. In Amazon Redshift, the primary resource is a cluster, but it also supports other resources that can be used with the primary resources, such as snapshots, parameter groups, and event subscriptions. These are referred to as sub-resources. So the cluster resource as well as the sub-resources can be, users can authenticate to these resources using IAM credentials. Especially for databases, you can use your same IAM credentials to generate database credentials and authenticate your users using those credentials. If you already manage user identities outside of AWS, you can authenticate those users for access to an Amazon Redshift cluster by integrating the IAM authentication and a third-party SAML 2.0 compliant identity provider, such as AWS, Ping Federate, or Okta in your environment. And these concepts are very well explained in a blog as well as in the Redshift documentation. So in terms of authorization on Redshift, again, IAM permissions can be established for copy, unload, create schema, and other commands. We highly recommend that you implement role-based access control, where the cluster assumes a IAM role on your behalf to execute commands. Although you can go with key-based access control, this is not a recommended approach. To restrict access to databases, you can leverage the grant command, where you can create a group of users and grant access on schemas or databases to those specific groups or groups of users. So in terms of resource isolation, you can implement separate schemas and databases, as we discussed in the previous section, where the data can be partitioned via a column that represents a unique tenant identifier. You can also leverage the workload management component of Redshift that allows you to define different query queues for different users, groups, or even priorities. Queries are routed to these queues according to their priority or users or query groups. And for each of these query queues, you can configure multiple parameters, such as concurrency level, the user groups, query groups, the WLM memory percentage to use, the timeout that you specify in case the query doesn't finish at a certain time, query hopping, as well as queue monitoring rules. When it comes to implementing multi-tenancy with serverless services like Amazon Athena and AWS Glue, it is important to consider what the resources exactly are with these services. So for example, for Amazon Athena, the console, the Athena console and the JDBC connector could be considered the resources, and authentication to these resources can be implemented using IAM users, groups, or IAM roles. Similarly, for Glue, the resources are the Glue tables and the Amazon EC2 instances where Glue runs, and the authentication mechanism for that is through the IAM users and IAM roles as well. So in terms of authorization in Amazon Athena, for console and JDBC-based actions, IAM policies can be attached to IAM identities. For Amazon S3 and Amazon QuickSight, IAM policies, S3 bucket policies, as well as cross-account permissions come into play to implement authorization. In Glue, identity-based policies can be attached to users or groups in your own account, and you can also attach permission policies to a role and grant cross-account permissions. So lastly, let's take a look at how multi-tenancy can be implemented in the ingestion service, Amazon Kinesis Data Streams. With Kinesis Data Streams, authentication and authorization, again, is enabled through IAM. IAM can give you control to access the Kinesis Data Streams API actions, as well as policies that can be attached to your IAM roles or groups to access the Kinesis client library, which includes permissions to DynamoDB and CloudWatch as well. There are certain considerations to look into when you are implementing multi-tenancy with Amazon Kinesis Data Streams. For example, for a silo mode, you can create separate streams for each producer, which means that each data producer is writing to a different stream. and the consumers can read from the shards in their own stream. If you want to implement a shared model with Kinesis Data Streams, producers can still write to a single stream, but when they write these records, they can write to a specific shard using a neat feature in the Kinesis Data Streams called explicit hash key. The explicit hash key allows these producers to direct their messages to specific shard, allowing the consumer to read from that specific shard. You can also write records with a unique ID, and the destination store or a KCL-enabled application can separate them out using the unique column ID. The shared model with Kinesis Data Streams can be implemented in customer environments using what is called a fan-out design. In this design, multiple producers can use the AWS SDK to write to different streams, and the data pertaining to those streams can be read by the Kinesis-enabled application or the KCL app, which in turn reads those messages and directs them to streams pertaining to different tenants. This architecture gives a lot of flexibility in fanning out these messages to separate streams, allowing the tenants to consume messages from their own streams. So this concludes this webinar, and we are happy to take your questions now.